Hi, everyone. Thank you for the invitation to give this seminar. So today I'm going to present some work that I did in collaboration with Astrid Eikholm and Ras van Guraal here in Heidelberg. So I know that you mainly know what the first part of my title means, gravitational universality classes. But well, order-4 random tensor models is something maybe a bit more tricky or unknown in this community. So I'm going to spend the first part of my talk explaining what I mean by that. So let's start with it. So random tensors, and why do they have to do anything with quantum gravity? So in quantum gravity, we know that we have our path integral, or here I am writing the Euclidean path integral already. I'm not going to say anything Lorentzian. You can ask me at the end. But well, here I am writing my Euclidean gravitational path integral. And well, we know that this integral is describing really fluctuations, quantum fluctuations of space-time itself, of geometry itself. And in order to grab a better handle over it to, for example, control the geometric degrees of freedom that arise from this path integral, also in order to think about a more background independent way of defining this path integral, there are many reasons why one would want to discretize this path integral, okay? You can choose your favorite. And this is not anything new. It was already taught by Recce in the 60s. And there is a whole area called Recce calculus, where one works with the discretization given by of this path integral. And there is also another instance of this called dynamical triangulations, okay, where one works, again, discretizing this path integral. And the main idea is that, well, I am trading the continuous degrees of freedom given by the metric in the usual geometric picture for how I am, well, for now some discrete degrees of freedom. And these are going to be codified by, for example, if I fix the lengths of my building blocks on ways in which I can glue these building blocks together to create something, at least something that looks a bit like a manifold. So in 2 dimensions, this is going to look like, well, the gluing of triangles, hence the name dynamical triangulations. And in higher dimensions, my building blocks are going to be, well, higher dimensional. And my path integral is really going to tell me, it's really going to count how many ways of gluing these d-dimensional building blocks I have, okay? So given this idea of discretizing the path integral of gravity, I want to study some theories that are given by this discretization, okay? And one way to discretize the path integral for gravity is exactly using random tensors. And I'm going to explain now exactly how. Okay, so let me first introduce what a tensor is. I know that most of you are very good working with tensors, but let me tell you exactly what kind of tensors I am talking about. So a tensor is going to be, as you know, this thing with d indices. That's a d tensor. And each index can go from, well, I could choose it to be from 1 and go from 1 to capital N. So for example, a matrix is going to be something that has 2 indices, and each index goes from 1 to n. So I have an n by n matrix. So this is the higher dimensional analogous of that. And the kind of tensors that I will be interested in are some that are invariant under certain symmetry. And this symmetry is an ON to the D symmetry. And what that means is that my tensor with the indices A1 to AD is going to be equivalent to the tensor where I transform each of the indices individually, okay? What that means is that each of these indices is kind of independent or has its own color, it cannot be exchanged with indices in other positions, okay? It has like a symmetry space that it's, that needs to be respected, okay? So for example, I cannot change A1 and A2 like I would do with other kinds of tensors because I have this symmetry, okay? So the place of that my index has to be respected. So as I said, this gives the tensor the property of being a color tensor because I can just choose a color to assign to each of these indices, okay? Since they are to remember graphically that I cannot mix indices in the I and J position when I is different from J. So for D equals 3, so for an order 3 tensor, I will have my tensor that I call T, and I will have my 3 indices, okay? That I depict with a different color to remember in which position they are. For D equals 2, for an order 4 tensor, I will have a tensor with 4 indices, and I keep track of my colors to remember which is the position of my index, okay? Or which index it represents. So these are what color tensors are. And now let me tell you what the random part of the tensors is, okay? So if I already gave you an object, and if I tell you that something is random, well, I have to give you some probability distribution associated to it. Or in physics words, I have to give you a partition function, okay? And the partition function, well, is determined by the symmetry of my object, which I know what the symmetry is, and also the exponential of an action. So I need to tell you how to construct the action, and I want this action to be invariant under my symmetries. So the way to do this is, for example, let me go to order 3 tensors. I have my building block, my field, okay? The variable that is going to be summed over in the partition function is T. It has 3 indices that are colored, and I need to construct invariant things over the symmetry. So the only thing that I can do is actually contract my indices accordingly, okay? So for example, this is going to be my only invariant term of order 2. So it has 2 tensors, 2 fields. It's a quadratic on the field. And I make it invariant under the symmetry group by contracting the indices accordingly, okay? First index with first, second with second, third with third. And this actually corresponds to something that is the trace of T square. And graphically, it's represented in this way, okay? If I want to go an even number higher, then I will have interactions of order or invariants of order 4. So I need to have 4 tensors. And again, I need to construct things that are invariant under the symmetry. So I need to contract the indices again in all possible ways, such that I don't have 3 indices at the end, okay? Or that it transforms trivially under this group. And the terms that I'm going to get in this case are of 3 types, okay? I'm going to get a trace that is the trace of T square. So this disconnected contribution. And I'm also going to get other types of terms. So this is, for example, something called the pillow, and this is something called the tetrahedron, okay? So again, when you see T's, you should really be thinking in your usual quantum field theory about a field. So these are really quartic interactions that are weighted by some coupling constant, okay? And it just so happens that because I have a field with indices, there are different ways to construct a quartic order interaction, okay? So now, for example, we can go an order higher. So for D equals 4 or order 4 tensors, our field is going to be this T with 4 indices, and each index has its own color. And then again, I want to construct something that is invariant under O to the 4, On to the 4. So again, the only quadratic term that I can construct is this one, okay, which has this graphical representation, which is just trace of t to the t squared, trace of t squared. And now the order 4 interactions or the quartic interactions that I can construct are these 4, okay? And here, when I had d equals 3, I could only construct these 3 interactions, okay? The double trace, the pillow, and the tetrahedron. But when I increase the order of my tensor, now I can construct 1, 2, 3, and 4 interactions, okay? These are all the invariants under the symmetry that are of order 4 that I can construct. So this is how one constructs the action for these random tensors. And this gives me, well, the partition function. So the recipe to sample these random variables, these random tensors. And this is what defines my random tensor model, okay? So if I am telling you that I'm giving you some partition function where I have a field and I have some quadratic part and some interactions, then you can ask me, well, what are going to be the Feynman rules for this system, okay? So in order to construct some Feynman rules for this theory, then what I need is, well, to understand what is the 2-point function of the system, and, well, in order to construct my big rules, okay? So, or my big contractions. So my action in the case of t equals 4, so 4-order tensors, is going to be some quadratic part. And actually, this quadratic part, I can write it exactly like this. So I'm going to contract first index with first index, but I write it with a delta in this form. Second index with second index, which is given by this delta, and the same for the other two indices, okay? So I can see that I have my 2-point function, at least the bare one, is going to be given, well, by my 2 tensors, given contracted by this tensor structure, okay? Just how you would have it in field theory, in usual field theory, is just that here my field, this T, just has a lot of indices. So I have to take care of what these indices, how they contract, okay? Another thing that you can realize here is that I have no P dependence, no momenta dependence in the propagator. And that is because my fields, they are 0-dimensional. So they don't depend on position, they don't depend on momenta. They are 0-dimensional fields. So the only degree of freedom that they have is their index and how I contract my indices, okay? So in other words, this is a combinatorial model. If you're more comfortable with it, it's a 0-dimensional quantum field theory, okay? That's why my propagator is only this delta function, these chronicle deltas, okay? And there is no integrals or any momenta or any continuum variables, okay? So I have my propagator, and then these quartic parts, I'm going to consider them as interactions. Okay, so if I have my interactions and each of these interactions has a coupling constant, I have my propagator that tells me how to contract things. Then I can construct my Feynman diagrams. Okay, so I have interactions. My interactions, instead of looking point-like, like in a quantum field theory, in a usual quantum field theory, they would look like, they actually look like these trace invariants, just because of the symmetry of the problem, okay? So this color thing is an interaction. It's a 4-point quartic interaction. And these dashed lines are the propagators, okay? So here I will have a diagram that will go as G2 squared. G2 is just a coupling constant that corresponds to this interaction. So G2 squared. And I have to implement my big contractions. And my big contractions, the only thing that they are going to do is that, well, they are going to make sure that I contract the indices in the right order to respect my Owen symmetry. And for example, in this case, I will have my I have the color 4 here in this loop. And I have color 4 here, and my propagator tells me that I just need to identify this color 4 with this color 4, okay? And in order to obtain something that is colorless, okay, so I need to sum, instead of summing over or integrating over momenta, what I need to do here is sum over the indices. These are my only degrees of freedom, okay, to compute this amplitude. So then when I have these loops in my Feynman diagrams, what I'm going to get are factors of n. N, remember, is the size of the tensor. So in a matrix, it would be an n by n matrix. In a tensor, it's an n times a lot of n's tensor. So when I sum over the indices, the maximum I can get is n, okay? So the trace, then the number of components of the tensor. So every time that I have loops, I will get factors of n. That's what I want you to remember. So then the amplitudes of these graphs actually have an expansion in n, okay? And there is a precise way in which these amplitudes scale with n, with the size of the tensor. D is the size, the order of the tensor, and there is a positive number that depends on the graph structure. But this is not important for what I'm going to say. What I just want you to remember is that all of the amplitudes, all of my Feynman diagrams depend, well, scale as some powers of n, okay? So now let me go more, if this has been too abstract for you, let me go to now, well, what is the geometric interpretation of what I have been telling you so far, okay? Because remember, what I wanted with the statement with which I started this talk is by saying that the random tensors are one way of discretizing the path integral in quantum gravity, okay? So now I can, we can see the random tensor, so this T, this field, this zero-dimensional field T, which in the case T equals 3 has 3 colors, okay? So I have my 3 colors and I have the propagate, which are the big contractions, okay? The rules to glue together the tensors and to construct my Feynman diagrams. Now I can think of on a dual picture where each of these colors actually corresponds or are the Poincaré dual of some higher dimensional things, in this case, some 2-dimensional triangles. So what looked like it had like no geometric structure here is actually dual to a tetrahedra for the equals 3, okay? Where each of these legs transverse one of the faces, one of the triangles of the tetrahedra perpendicularly. And this tetrahedra is not just any tetrahedra, but it's a tetrahedra that inherits the coloring of these indices or of these lines of the tensor, okay? So in other words, when I have a D tensor, okay, so a tensor with D indices, plus its propagator, plus the big contraction rules, this is equal, or this is dual to a D-dimensional building block and some gluing rules. So in this case, you can see here I have a tetrahedra where the 3 colors correspond to 3 of the faces of the tetrahedra, and the extra face, the 4th face, actually is going to be colored by the propagator, and it's just going to tell me exactly how to glue a tetrahedra together. And this is not just a pictorial representation, but it is actually proven that D+1 color graphs, where it's D indices come from the tensor, 1 from the propagator, or this dashed line, are equal or have the same expansion as triangulations of pseudo-manifolds of dimension D, okay? So really these D of the tensor, the number of indices, can be thought as the dimension of the pseudo-manifolds that you produce by gluing these building blocks together. And more than that, it has actually been shown that the partition function of these D+1 colored tensor models, in the way that I showed you by constructing invariants, can be written as some in the form of some discrete gravity path integral, and well, this form is just the form that you would expect. It's a Recce action. Okay, so I am not going to tell you anything more about these proofs. What I just want you to get from this is that working with D+1 color graphs or D+1 random tensors is really going to be just working with triangulations of spaces of dimension D. Okay, so now this is still discrete. So when I tell you here, this is proven at the level of triangulation still of a pseudo-manifold dimension D. So this is still discrete. The building blocks, finite size building blocks, are still there. So in order to make some contact with quantum gravity in a more infrared perspective or classical language, one has to take something called the continuum limit, or in other words, taking the number of building blocks to infinity and taking the size of building blocks to 0 while keeping the total volume fixed, okay? And what that means, you can think of this literally as zooming in or out, well, in this case, zooming out from a photo. So I have my photo, and I don't want to change the total volume of this photo. It's a fixed area in this case. And here I have my building blocks, these squares, that are still quite big, and there are not enough of them to have enough resolution. I can increase the number of these building blocks and diminish their size, and now I get a better picture. And well, hopefully, when I take my number of building blocks very, very big and the size of them very, very small, I will get a continuum picture, okay? And I will be able to translate my discrete degrees of freedom into some continuum picture. So this is literally what one has to do when working with these models. So for random tensor models, again, so my number of degrees of freedom is the size of the tensor. So how many entries, how big the tensor is going to be. And the quantity that I have to keep fixed is this n to the power of d-2 times something that has to do with a coupling constant. Okay, so these g's, remember, these g's are the coupling constants of each of the tensor invariants. And the idea is that, well, the second condition, that the size of the building blocks goes to 0, actually gets translated in just, well, these coupling constants reaching a critical value, okay? And this is a quantity, this is the analogous of keeping the total volume fixed, or the total area in the example with the picture before. So this is, this has been well understood for some time. And now let's think about what this means. So taking n to infinity, what that means is, well, the size of my tensor will increase. So these are many degrees of freedom. Okay, so by taking n, I have to move n, and I want to take some, well, again, many degrees of freedom. That sounds a lot like a renormalization group scale, where I want to vary these to reach some regime. And exactly the regime that I want to reach is, well, I want to reach critical regime, okay, where my coupling constant takes some critical value. And well, this sounds a lot like reaching a fixed point of the system. And if this is the case that I can actually take this continuum limit where I have some renormalization scale and I want to find a fixed point, and my random tensors per se, they describe a sum over triangulations of pseudo-manifolds weighted by some gravitational action. The big question is, well, is this universality class coming from random tensors compatible with that of asymptotically safe quantum gravity? Okay, so if you were wondering all of this time why I was giving this talk in this seminar, it is because of this. This is the connection with what most of you are doing. So in order to answer this question, I will, in this talk, I will use the FRG. Okay, so, I will use the FRG. So let me give you some dictionary between what the FRG that you know is or how it looks for these zero-dimensional models, okay? So in your QFTs, you have a renormalization group scale, which is called K. And this is the K that, well, that the UB is going to correspond to K going to infinity. And in zero-dimensional models, again, I don't have any momenta, so I cannot choose a K in the same way, but I have the size of the tensor. And this tensor, the size of this tensor, the number of degrees of freedom going to infinity, is what I'm going to call the UB in this case, okay? So this is where I'm going to be looking for my UB fixed point. In QFT, you have a derivative expansion, okay? Because, well, you have a d-dimensional theory, so you can actually count how many powers of momenta or of position, of space you need to, in order to make your action act as, well, dimensionless, okay? So you have your derivative expansion. In this case, I don't have that because, again, it's zero-dimensional. But in this case, I have my trace invariants, okay? So I have a trace invariant expansion in the same way that we constructed our action before, saying, well, first, let's look at the quadratic interactions I can construct, and let's look at the quartic interactions I can construct, and I look at all of the invariants for that order that I can build, okay? And then in QFT, you have your dimensionless couplings that you can construct just by multiplying your dimensionful couplings with the corresponding corresponding inverse of the dimensions of the operator to which it is multiplied. Okay. In this case, again, I don't have momenta, so I don't have a canonical way of constructing dimensionless couplings. But as I mentioned before, my amplitudes have an expansion in n in this parameter, and they are G-scale. So actually, when I compute beta functions of these couplings, I will find a lot of powers of n to some powers coming, remember, from these loops in the Feynman diagrams. And the dimensions I can construct dimensionless couplings just by demanding that my beta functions have a 1 over n expansion. Why? Because then I want to take n to infinity, and things that go as 1 over n are going to vanish in the large n expansion, okay? So this, by the way, this dictionary, this original idea comes from Bredzin and Sinjostan about taking the renormalization scale of these combinatorial models or these zero-dimensional models as n. But Eichhorn and Kozlowski are the ones who actually constructed this dictionary. Okay, so I'm going to leave my dictionary here just so you remember what the analogous is for these zero-dimensional models. And now I want to see, well, what the Betterish equation is going to look like. Well, the answer is that it's going to look exactly the same. Just remember where you had k before, okay, you have to put n. So now I'm going to have my RG scale here. I still have my logarithmic the logarithmic variable that you always use in this equation. I still have a effective average action and I have a regulator, okay? So it is exactly the same as in usual QFT. Just remember this dictionary. So now, in particular, what I'm gonna show you now is what we did. So we worked with an order-4 tensor and order T to the 8 truncations. So what does this mean? So order-4 tensors, that means that I am producing 4-dimensional triangulations or triangulations of 4-dimensional manifolds, okay? So these will be gravity in 4 dimensions, and I am using quote unquote. And what the truncation that I'm gonna use, so in other words, in my derivative expansion, I will use operators of order at most 8, okay? So I will have all of the interactions that I can have with at most 8 of the fields, okay? So I will have T to the 8 truncation. This is a truncation that was used already in this paper by Astrid and collaborators, and And yeah, so again, this is the action that we constructed together at the beginning of the talk. So we have quadratic term, quartic, my 4 quartic interactions. And then I'm gonna have also sextic interactions. So with 6 fields, this is of order T to the 6. There are also 17 other interactions of order 6 that I am not drawing here. And in order to go to T to the 8, there are 6 of order of operators of order 8 in this truncation that again I'm not writing here, okay? So this is a system, this is an effective average action with 30 couplings. Yep, so this is a system that I'm gonna analyze. And now for the regulator, for my FRG, what I will use is an IR regulator a la Litin, but it's going to be, well, it's going to be deformed. It's going to be parametrized by 2 parameters, alpha and R. So now this is, maybe you don't recognize it immediately, but this is Litin's regulator almost. So here what you have as N, remember N is like some momenta. A, B, C, D are indices of the tensor. So so here this N over the sum over indices is like what you have in continuous, well, in QFT, that is K over P or P over K. I never remember what's the right one. But yeah, this is literally just P squared. I think you call it P squared over K squared, okay? So this is just going to be, you just go to your dictionary and you can find that this is actually Litin's regulator for alpha equals to 1 and R equals to 1. Now, when you vary alpha and R, what you find is that, well, alpha is going to modify the overall scale of your regulator. So this is for alpha equals to 1 and for alpha equals to 100, for example. And what R does is that it changes the shape of your regulator, okay? So this is for R equals to 1 and R equals 2.5, okay? So it changes the slope of the regulator. And again, here in this image, the x-axis corresponds to the sum of the indices of the tensor over n. So this sum goes to 4n. So this 1 here corresponds to this sum equals to n. And these are just going to be the indices that are on the top right corner of your tensor. So if you think about a matrix, an n by n matrix, okay, this x-axis is just going to, before up to 1, is just going to be the indices of, well, the components of your matrix that are on the top left corner of your matrix, okay? So what I want to do with this alpha and R, with this regulator, is that I want to incorporate the principle of minimal sensitivity. Okay, so what that means is that I'm gonna, well, compute beta functions as usual. I'm gonna find fixed points and critical exponents, and I want to find the extrema of these critical exponents in this parameter space alpha, expanded by alpha and R. So why would I want to do exactly that? Well, because in 2019, this random tensor model of order 4 in the truncation t to the 8 was studied for alpha equals to 1 and r equals to 1. And what they found was a fixed point. And this fixed point has the first two critical exponents that are compatible in their numerical values with the Reuter fixed point, okay? So the Reuter fixed point has these first two critical exponents between 2 and 4. So this is compatible with that. And what they found is that this third critical exponent, actually, it starts being negative. It becomes more negative in the next truncation, so in the t to the 6 truncation. And then when you increase the truncation, this becomes less negative, okay? So it is not monotonically decreasing or increasing. And the question was, well, at first glance, it seems like this is incompatible with the Reuter universality class because you would like to have 3 positive critical exponents, and this one seems negative. But, well, we don't, since it is not monotonically increasing or decreasing, the question remained of, well, is this going to become positive at some point or not? Furthermore, there were, when you reach the order 8 truncation, there were other fixed points that were found where the first 2 critical exponents, they are positive, their numerical values are compatible with the Reuter universality class, but they were not included in this paper, so in the 2019 paper, because their distance, the Euclidean distance in the coupling space is bigger than of this critical point that was described there, okay? So in other words, this critical point, this fixed point called A, that was the one reported here, seems like the continuation, the natural continuation of these fixed points found as smaller truncations. And that's why these fixed points B and C were discarded then, okay? But now I will consider these 3 fixed points, okay? But now for alpha and R different from 1. So now these are the new results. So this is my fixed point A, so the one that was found in 2019. You can see the values exactly at the R alpha and R equals to 1, or in other words, with the usual lithium regulator here with a star. And now you can see how the critical exponents look in the alpha R space, okay? And as you can see, the first 2 critical exponents, the real part, it remains still between 2 and 4. So they remain at good numerical values to be compatible with the Reuter fixed point. But the real part of the third critical exponent, it remains negative, okay? At least in this part of the alpha R space. But now something more interesting came out when we were analyzing now the fixed point B, which was not reported in 2019. So again, here are their values for alpha equals to 1, R equals to 1. So in this case, the first 2 critical exponents, the real part, again, it remains and good numerical compatibility with the Reuter fixed point. But the third critical exponent, it's actually positive in this region below this pink line, okay? So this fixed point B, is actually a fixed point with 3 relevant directions, okay? So at first glance, it would seem it was a bit weird that this was discarded, because this is exactly what they were looking for, right? They were looking for a fixed point that had 3 relevant directions, and this fixed point B has in fact 3 relevant directions. Now, something very interesting happens. So if you see above the pink line, this fixed point A and fixed point B, the values for the critical exponents, they look exactly the same. So the graphs look exactly the same on top of this pink line. Underneath, they are different, but on top, they are the same. So you should be comparing here vertically. Now, what this means is that, the first thing that comes to your mind when you see something like that, and you have been looking at beta functions for a long time, is that there is a fixed point collision, okay? So now we analyze this fixed point collision for fixed values of alpha and R. Remember, these are my 2 parameters in my regulator. And in fact, what we found is that the fixed point A and fixed point B, they undergo a fixed point collision at finite values of R and alpha, okay? So this just corresponds to this, to these pink lines. So I am looking at a projection of these pink lines. And so there is, in fact, a fixed point collision. And as you can see, these are the first 2 critical exponents, okay? Which again, there's no problem with them. They remain between 2 and 4. So they are compatible with Reuter. The third critical exponent, though, it undergoes you have this fixed point A, which has a negative critical exponent, okay? And this fixed point B, which has a positive critical exponent, but they undergo a fixed point collision, and then both of them become negative. So let's look a bit more at them. So the fixed points are real between these two, between the fixed point collisions. So in this region where there's one positive and one negative, one relevant and one irrelevant direction for each of the fixed points. And the fixed point is complex before and after the fixed point collision. And the lines that I am showing you, before, these vertical lines are actually the minimal sensitivity values for each of the critical exponents, okay? So again, these minimal sensitivity values are the extrema of the critical exponents with respect to alpha and R, these parameters in the regulator. So these values selected by the principle of minimal sensitivity for R and for alpha, okay, in these projections. So for R, we can see that the values are very close to 1, okay, for alpha equals to 1. And for R equals to 1, alpha, it is between 1.5 and 2, okay? So again, alpha equals to 1, R equals to 1 is the usual lithium regulator. And you can see that the optimal values of the values of the critical exponent at the optimal parameters are not very different from the values that were found in the 2019 paper. So for alpha equals to 1 and R equals to 1. But again, I mean, we have that the principle of minimal sensitivity actually chooses these this positive critical exponent for fixed point B. So again, fixed point A was the one that was reported in 2019. Fixed point B is a new reported fixed point, and it has 3 relevant directions. Okay, but they undergo a fixed point collision. So now we have another fixed point, the fixed point C, and this fixed point, this fixed point is real. Its first 2 critical exponents are compatible with Reuter's universality class. The third critical exponent is negative, so it only has 2 relevant directions. And there is also some values selected by the principle of minimal sensitivity. Okay, so we have this fixed point C that seems to be very stable, or at least it doesn't go any fixed point collision. And we also check the limit of a vanishing regulator, okay, that has been used in other computations in asymptotic safety. So this corresponds to alpha going to 0. And well, we found that the only fixed point that survives in this limit is exactly fixed point C. That means this is the fixed point that doesn't collide with any other fixed point, okay? So this fixed point C seems to be pretty stable in the whole parameter space. Fixed point A, which was reported in 2017, is not. 2019, sorry. Okay, so let me just do a recap, okay? So the big question was, well, I have these random tensor models, and they are a way of codifying the path integral for quantum gravity in a discrete way, okay? So when I take this continuum limit, is the universality class of random tensor models compatible with that of asymptotically safe quantum gravity? Okay, this was the big question. So for this, we studied the fixed point structure of this order-4 random tensor model. The 4 means 4-dimensional triangulations. And what we found are 3 fixed points with 2 out of 3 critical exponents compatible with the Reuter universality class, okay? But only one of them is real across the full range of these alpha and R parameters. And this is called, we call it fixed point C. This fixed point was not reported in the original study of this random tensor model in 2019. But even so, 1 out of the 3 critical exponents of this fixed point is not compatible with the Reuter universality class, because as far as I understand, the Reuter universality class has 3 relevant directions, okay? So what is is the universality class of random tensor models compatible with that of asymptotically safe quantum gravity? Well, not so far, okay? That's the question. That's the answer, sorry. So on the outlook, I mean, we have some to-do list of very minimal to-do list. I mean, on the technical side, well, you know that going to higher order truncations, it's, well, when you see things that don't seem quite compatible with what you would expect, well, going to higher truncations is a natural first step. So we want to go to higher order truncations to check if these fixed points A and B, that are the ones that cause this fixed point collision, are truncation artifacts, okay? Or if they actually become real. Because in particular, fixed point B has 3 relevant directions, which is what we want. We would also like to look for new ways of reaching the new universality classes, okay? So, or to find universality classes with 3 relevant directions, but by looking more at the structure of the tensor model, at the random tensor model, okay, or at the types of geometries that it produces. And one way to do that is by imposing causality using something called a dually weighted structure, which I won't talk about here. And another thing that I is the one that I am excited about right now, is to introduce a proper notion of curvature in these models. Why would we want to do that? Well, because as you may know the three relevant directions in asymptotically safe quantum gravity in the pure without matter, matterless case come from the Ricci scalar, the cosmological constant, and the R-squared term, okay? So you have one higher curvature term that seems to become relevant and in the UV. So the question is, well, how do I track this higher curvature invariance, or in general, how do I track curvature in these combinatorial models that only tell me about how to glue building blocks, okay? And these building blocks are flat. So what we have started doing is, well, trying to put this in a, to understand what measuring curvature would mean in these discrete models. So to exemplify that, and this is my last slide, don't worry, is that in V equals 2, so you have three color graphs or two-dimensional random objects or geometries, okay, so surfaces. It's also called a color matrix model. So you will have that your tensor, okay, has two indices, two colors, plus the propagator here. And then what means gluing or constructing invariance is to, well, match all of these or connect all of these colors together to have something that it's invariant, okay, under my symmetry, just as we did with D equals 3 tensors, D equals 4 tensor. What that means in the dual picture, so in the geometric picture, is gluing all of these triangles in a good manner, such that, well, I respect my colors. And then actually, when you are in this dual picture, you will have vertices here, and the curvature, the scalar curvature at these vertices is actually just related with the deficit angle. So you will have that your curvature, if you have these equilateral triangles, you have a flat configuration if there are 6 triangles that meet in one vertex, okay? And if you have less than that, well, then you will have a positively curved thing. And if you have more than that, you have a negatively curved thing, okay? So this number becomes positive, 0, or negative, depending on how many triangles meet at this vertex. And as you can see in the picture with the colored graphs, it's going to be measured by the length of bicolor cycles, okay? So this is a combinatorial structure in the graph. And we think that this is generalizable to higher curvature invariance and to D bigger than 2. So that you can, in other words, you can construct the Ricci square, and the Ricci more and more by using this structure of the color graph, okay? And this is work in progress, so stay updated for that, okay? Thank you.
Thank you very much, Alicia, for the nice talk. Sorry.